Welcome to our next lecture in the series on condensed matter theory. In this video I want to have a look at the non-local Green's function of an infinite one-dimensional chain. And we'll take as a basis again the 1s orbital or an s orbital such that our Hamiltonian is given by a sum over all lattice sites, an on-site energy given as epsilon s, and then hopping between nearest neighbors, site j and j plus 1 or j plus 1 to j, with an hopping strength as a sigma. We want to calculate the non-local Green's function. So what we want to calculate is given by g, where we annihilate the particle at rj after we have created the particle at site I. And this is given by the expectation value of creating the particle at site j, 1 over omega minus the Hamiltonian plus I0 plus, and annihilating the particle at site I. We can also look at this as elements of the full Green's operator on the basis of the local states, where you look at element ij of this matrix. In pictures where the lines indicate our hopping and the circles the sites, we have our site, somewhere we have site I, somewhere we have site j. And we look at creating the electron at site I and having it propagate to site j. In order to solve this problem, we will separate our Hilbert space in different parts. Part A represents a finite one-dimensional chain, starting at site I going to site j. And then we have a Hilbert space B, which consists of a part B plus and a part B minus. Now the only coupling that we have to B plus or B minus is the coupling that we have via the interface to the first site. So we are interested in B plus of site R j plus 1 j plus 1 omega, which is the Green's function of a semi-infinite chain, and the same the Green's function from B minus Ri minus 1 Ri minus 1 omega is the Green's function of a semi-infinite chain, or the endpoint of a semi-infinite chain. And then of course what we also need as an ingredient is the Green's function for a particle propagating within A, and the Hamiltonian for Hilbert space A is given by a sum over the lattice sites in A, going from I to j, epsilon s a dagger k a k plus the sum, k is I, to j minus 1 as a sigma a dagger k a k plus 1 plus a dagger k plus 1 a k. And in all this we have assumed that I is smaller than j. We can easily do the same in the other case. Now before we will solve this for a general length finite chain, so a general difference between I and j, let's have a look at the case where the chain has length 2 and 3. For the case where the chain has the length 1, you create and annihilate the particle at the same site, and this we solved in one of the previous examples. So for the case where n is equal to 2, we know that j is equal to I plus 1, and we can write down our Hamiltonian in matrix form. And for subsystem A, this is nothing more than epsilon s for the onset energy, and hopping between side I and j, and an epsilon s for the onset energy again of sides j. We can now look at the Green's function for subsystem A, and I will give it an extra index relating to the fact that the length of our finite chain is 2. It's an operator, so we look at the full matrix within Hilbert space A, and this is nothing more than omega minus HA plus I0 plus, and as we have the matrix and it's just a 2 by 2 matrix, we can solve this. Minus SS sigma minus SS sigma of the off-diagonal part, omega plus I0 plus, minus epsilon s, and then we have to do a matrix inversion, and this we can write as omega minus epsilon s plus I0 plus, SS sigma, omega minus epsilon s plus I0 plus, times 1 over omega plus I0 plus SS sigma omega plus I0 plus minus epsilon s minus SS sigma. Now, we do not only need the Green's function of the semi-infinite chain, we need the Green's function of the the finite chain, but we need the Green's function of the finite chain embedded in the infinite chain. So we want to look at the full Green's operator, but this is in principle an infinite by infinite matrix, and we're only interested in the elements that belong to subsystem A. And this is given as 1 over, and now we have the propagation of the subsystem A minus 1 minus how you couple between A and B, and then propagate in B, H, B, A. So we have here two Green's functions. They're both given by 2 by 2 matrices because the dimension of A is 2, but they have reasonably different in their meaning. The first one is a finite system only. So this is truly a Green's function of a 2 by 2 system. The second is the Green's function of the full chain, but elements in A only. So out of this infinite by infinite matrix, you look at elements A. In the first case, your Hamiltonian is an infinite by infinite matrix. You take the elements that belong in subsystem A and you invert. In the second case, your Hamiltonian is an infinite by infinite matrix. You invert, or better said, you invert omega plus I0 plus minus the Hamiltonian. And you then take the elements A, A, or the elements that belong to subsystem A. So reduce and then invert, invert and then reduce. That's the difference. And it's of course this one that determines your dynamics and that we are after. Our Hamiltonian HAB couples side I with I minus 1 and side J with side J plus 1. So we do not need the full propagator and all its elements in subsystem B. We only can excite to state I minus 1 or state J plus 1. So we only need out of our full propagator in subsystem B the subspace or the elements I minus 1 and J plus 1. And we need both the creation and annihilation on I minus 1, the creation on I minus 1, the annihilation on j plus 1, and j plus 1 to j plus 1, or I minus 1 to j plus 1. So we need this 2 by 2 matrix. Now, as the positive and the negative lead do not interact with each other, this is a 2 by 2 matrix where you can add and remove a particle to the lead with negative indices, or you can add and remove a particle to the lead with positive indices. And the same is true for the Hamiltonian that couples side A with B. And here we can either hop from side I and j to I minus 1 and j plus 1. And this matrix is as a sigma 0, 0 as a sigma. I hops to I minus 1 with hopping matrix element as a sigma j to j plus 1 with amplitude as a sigma. So our full Green's operator, when we look at the elements belonging to A, so side I and j, or I plus 1, because j is I plus 1, is equal to the inverse of the propagator within side A, which is this matrix, omega plus I0 plus 0, 0, omega plus I0 plus, that's the identity, minus the Hamiltonian, epsilon s as a sigma, epsilon s. So this is the identity times the energy, slightly shifted, such that we know that our poles are in the lower half plane. This is the Hamiltonian within subsystem A, and then we have the coupling from subsystem A to subsystem B, and then the propagation in subsystem B given by the Green's function of a semi-infinite chain, and then the coupling back to subsystem A. And that's the full Green's function that we have. And all these elements are known, and you can solve it and plot this. And that's for the case when n is 2. Now let's do the case when n is 3 as well. So j in this case is equal to I plus 2. We can again follow everything that we did before. Our Hamiltonian for subsystem A is now given by a 3 by 3 matrix. The on-site energies are epsilon s for side I plus 1 and I plus 2. And we have an hopping between nearest neighbors only, so there is no coupling between I and j directly. Only by going via the intermediate state. Now what we want to calculate is the Green's function of the full system, or the Green's operator for the full system, restricted to the subsystem A. And that is just 1 over the Green's function of subsystem A inverted minus h AB, the Green's function of subsystem B, h BA. So this is the full system where we look at what happens when you add or remove a particle of subsystem A, and then we can here look at the Green's operator for subsystem A, which is 1 over omega minus HA plus I0 plus. So this is the finite chain only. Now of course we can invert a 3 by 3 matrix and get this directly. But then when you make your distance between I and j bigger and bigger, you have to invert bigger and bigger matrices. And actually there is no need to invert 3 by 3 matrices. We can use this idea of separating our Hilbert space in different parts that we had before. Our Hamiltonian is the Hamiltonian for a 3-side system. So our Hilbert space is given by 3 states. Either a particle at side 1, particle at side 2, or a particle at side 3. And this is subsystem A of the full Hilbert space. Now we can separate this system further, and we say that the side I plus 1 belongs to subsystem B or beta, and the sides I and j belong to subsystem alpha. So this is side I and that is side j. If we now write down our Hamiltonian, then H beta is epsilon s, A dagger I plus 1, AI plus 1. H alpha is epsilon s, A dagger I, AI plus A dagger j, AJ. And the coupling between them is given by the hopping A dagger I, AI plus 1 plus A dagger j, AJ minus 1. And this tells you how you go from beta to alpha. Of course you have also the going from alpha to beta, which is the complex transposed of this matrix. In matrix form, we have H alpha is equal to epsilon s, 0, 0, epsilon s. H beta is just a 1 by 1 matrix. And the coupling between them is then a 2 by 1 matrix with the hopping amplitudes as a sigma. If we now look at our Green's function of subsystem A for a chain of finite length 3 and as a function of omega, and we do not want to look at all its elements but only the elements that belong to alpha. So we look at the element alpha alpha of this matrix, which of course alpha still has element I and j, so this will in the end be a 2 by 2 matrix. Then this is given as 1 over omega plus I0 plus minus the Hamiltonian of alpha minus the coupling from alpha to beta, then our propagation in subsystem beta, and then the coupling from beta back to alpha. And we can now fill in the matrices. Omega plus I0 plus minus H alpha epsilon s minus, and now the coupling between alpha and beta. So here we change the dimension of our system and we go from a 2-dimensional Hilbert space to a 1-dimensional Hilbert space, because we have only one state in beta. And then we go back to our 2-dimensional Hilbert space. Now, of course, this is not everything. We need to couple this to the rest of the system, in semi-infinite lead on the right and a semi-infinite chain on the left. And we do not have to do this for a 3 by 3 matrix, but we can stay on this 2 by 2 matrix, because we know that B does not couple to beta, and the coupling between B and alpha is just given by SS sigma 0, 0. SS sigma, this side couples to the semi-infinite chain on the right hand side, and I couples to the semi-infinite chain on the left hand side. Such that the Green's operator as a function of frequency now projected on the subspace of alpha, so state I and j, so a 2 by 2 matrix, but a 2 by 2 matrix cut out of the infinite by infinite operator matrix for the full Green's function, so it includes all possible intermediate states, is given by the Green's function that we have here. Oops, GA alpha alpha minus 1 coupling to B. And we can write this in matrix form as omega plus I0 plus minus then the Hamiltonian that we have inside alpha, then the coupling between alpha and beta, and then the coupling between our finite chain and the semi-infinite chains on the left and the right. And the Green's functions for those are the Green's functions of semi-infinite chains. And of course you have to hop back from the chain to your finite length chain. And everything inverted. So now we can take our results that we have for a chain of length 2 and length 3 with infinite leads on the left and the right side. So the Green's function of going from side I to I plus 1 or from side I to I plus 2. And let's see how we can generalize this for the Green's function between any 2 points of an infinite chain. So for the general case, we look at the Green's function Ri, Rj of omega. And we take that n is equal to I minus j plus 1 is the length of the sum of the length of the finite length chain that we have. And alpha are the states I and j. So we look at the Green's operator, alpha alpha, which of course includes more information than we need because it is in principle then the Green's function Ri, 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 Rj, Rj, Ri, and Rj, Rj as a 2 by 2 matrix. But when I know this one, I definitely also know that one. And that is given as 1 over, and then the Green's function of our finite length chain of length n as a function of omega, and we do not need all its elements but only elements that belong to alpha, inverted minus h alpha b 1 over omega plus I0 plus minus hb hb alpha. Well, h alpha b 1 over omega plus I0 plus minus hb hb alpha is nothing more than the coupling of your finite length chain to the semi-infinite change on the left and the right, and you're only coupling to the first state of that. So this is a coupling for the left and the right to a semi-infinite chain whose Green's functions are given by GS, which we've calculated in one of the previous videos. Now, in order to calculate this Green's function, we can use induction. And we have our state I and state J, such that we define our subspace A, and we define our subspace beta and the subspace alpha. And we can now write our Green's operator on subspace A for a chain of length n as a function of frequency, looking at the elements alpha alpha, so I and j, a 2 by 2 matrix. And we can write this as a coupling where we have the I omega plus I0 plus, our energy, minus the Hamiltonian of alpha, epsilon s, minus, and then the coupling from alpha to the rest, as a sigma, and what we couple to are the endpoints of a finite length chain, which now has a length of n minus 2. So what we have here is the propagator of a finite length chain of length n minus 2 as a function of frequency, and we add or remove a particle from the endpoints. So we just reduce the length. And of course we can do this, then again put this in until we have a chain of a finite length 3 or 2, and at that point we have the equations that we had before. Actually you can stop at a length of 2 and 1, because also for 1 it's just the on-site Green's function that we need. So and with this we have now an equation with which we quite generally can calculate the non-local Green's function of a one-dimensional infinite chain, where you say you have your finite chain that couples to two infinite leads, and internally it couples to a finite length chain of a length 2 shorter than what we had before, and everything else goes via the Green's functions of the system. So I hope to have shown you with a few examples how we can work with these kind of Green's functions, how we can separate the Hilbert spaces in parts, look at how you propagate through part of that system and how this system couples to the rest of the system. And this coupling to the rest of the system is very often called the self-energy. Of course, in a system like this, you would normally not think of it, like you say, well, I have an infinite chain, and then the propagation in that finite chain is really what makes up the physics, and the rest is just a coupling to an external path. But for more complicated models, this definitely will become the self-energy of your system. And in one of the next lectures we'll have a look at this order, and there the coupling to the scattering of the randomly distributed impurities indeed becomes a self-energy and then determines the lifetime of your particle. For now, thank you very much. We see each other in the next video. Stay healthy.